Okay, I like this problem just because it hits a point home, something that is super important with this equation, and for that matter, this equation too. So for both these equations, we have torque. And something that is super important is that this torque is for, we were just looking at uniform bars. It is not the applied loads, is not the applied torque. It is the internal torque that matters. So am I going to be plugging this 500 poundage for this section, or a combination of these two? No, we have to calculate the internal torque every time that we are plugging into these two equations. Alright, we know the outside diameter. We have, this is 1 inch, and we're trying to find the inside diameter. Alright, we don't know that. We have some constraints here. We have allowable shear stress equals 12,000 psi. And we have another one. Here's allowable rate of twist. This is not the phi, this is our theta. So it's going to have units of degrees per foot, just like I would expect. 2.0 degrees per foot. So, since I have both of these have the allow tag on it, these are both my constraints, I need to compare them before I even start the problem. Before I even start looking for D, I want to know what's going to be governing. Let me put rate of twist in terms of shear stress again. Now I can look back at this formula, and we already knew that phi over L equals theta, our rate of twist. So I'm going to just use that fact. I'm going to divide this L over and substitute for the rate of twist. So now I've given myself a new equation I could work with. I now can solve for tau. I'm trying to convert my allowable rate of twist into its equivalent shear stress so I can compare this shear stress with my other shear stress. Alright, 80 times 10 to the 6 psi is our new G. A radius, we have an outer radius. Here's my thought process as far as radius. I'm trying to get my limits here. I'm trying to find what's going to break my rate of twist first. So my inner is going to be a little more conservative. I don't even know that anyway. But even if I had it, I would want to use my outer radius. That's going to give me my greater shear stress. So that's going to be, well, 1/2 inch. Alright, and our rate of twist was 2.0 degrees per foot. And look, I have inches, inches, feet. I'm going to convert these into inches. So I have 1 foot over 12 inches. Let me plug this into my calculator. I get 6.667 times 10 to the 6th, a very devilish number, psi. Okay. So comparing this with our other number, this is 6 times 10 to the 6th. This is only 12,000. Probably chose a bad G, but anyway, we wanted to use our smaller constraint. So that's going to be this one. Our tau allow 12,000 psi. Alright, let's press forward. Now I'm going to use this formula. And now remember what this torque means. This torque means internal torque. We're going to have 4 different internal torques. We're not looking at the applied torques, we're looking at each segment. If I label these A, B, C, D, E, let me start with AB. So I know tau, I know T, I know R is going to be my outer radius, where we're trying to push it to the limits, the outside of a hollow bar that's going to be failing first. And our IP, that's where our unknown D is going to come into play. Let me plug in some of these numbers. 12,000 psi equals our first torsion. Let me draw a little side picture here. This first one's pretty easy. I could find the internal torque by just doing a free body diagram, of A to somewhere in the middle. Now this was 1,000 pound-inches. In order to counteract that, the internal torque has to be also 1,000 pound-inches in the other direction. Now we don't have to worry about sign here because we're just looking at magnitude. We're trying to find which of these four segments is going to break first, and that's what's going to determine our diameter. So I just want to solve for the internal torques first. Is probably a better idea. So let me scrap this idea for a bit. So tau AB, I can solve this equation for T. I have tau times IP divided by R. 1,000 pound-inches. So this diagram gave me this number. Now let me look at the next free body diagram. I have 1,000 pound-inches there, and I have 500 pound-inches here. Now sometimes you can do these diagrams in your mind, but writing it down can really help you. So now I want to find my internal torque. This is TBC according to my diagram. TBC added up with this 500 has to counteract this 1,000. Or in other words, TBC plus 500 pound-inches minus 1,000 pound-inches equals 0, because it's not actually moving. And you saw that for TBC, and that gives you 500 pound-inches. You can continue on for these next two. I'll do them quick. I see now I have to counteract both of these added to there. So I know my TCD has to be 1,000 plus 800 minus 500, and that's going to give me 1,300 pound-inches. And now we're almost to the other side of the bar, so it might be easier for me to scrap that idea and just look at the little knobby end. So my T5 was 800 pound-inches, which means that this has to be counteracted the other way. TCD equals 800 pound-inches. Alright, so I've kind of scattered it around here. We have our torques from A to B, B to C, C to D, oop, mislabeled that one, D to E. We have our four internal torques, so TAB equals 1,000 pound-inches, TBC equals 500 pound-inches, TCD equals 1,300 pound-inches, and TDE equals 800 pound-inches. Alright, now I'm going to go back to the idea that I scrapped originally. I wanted to have the numbers to plug in here before I went along and chugged and tried to find my diameter, which I'm looking for. Just to remind myself of my goal, I'm going to redraw my cross-sectional area. So this is 1 inch, and we're trying to find our inner diameter. So what does this mean for our polar moment of inertia? Let's deal with that for a second before we get onto our next part. Polar moment of inertia, this is going to be pi outer diameter to the fourth over 32 minus pi d inner diameter to the fourth over 32. So I plug in the numbers I got pi, I can combine the pi and the 32 and just say it's 1 inch to the fourth minus d to the fourth. Okay, so I'm going to use this fact in a little bit, so I'm just going to mark that as equation 1. I haven't been doing too much marking so far. Maybe this will help you understand why we use those markings in engineering, because sometimes we have so many equations we want to mark where we got what from and where. So now we have our tau, we have our IP, we have our shear stress, and our radius. Remember, we're using our outer radius here because that's where it's going to fracture first. Let me solve this for IP. That way I have a number on this side and I have my variable on this side, even though it's not isolated yet. 5/32, 1 times inches to the 4th. I'm keeping this for units' sake. And d to the 4th equals whatever our torque happens to be. We have 4 of them. We have our radius, that's going to be constant, 1 inch. And we have our allowable shear stress. This is back from the beginning. We had 12,000 psi. Let me solve this for d, and then I'll just plug in the 4 different torques. Okay, then I would do d to the 4th. So I add that over, subtract that over. 1 inch to the 4th. Makes sense that I have 1 inch to the 4th minus something, because when we do the 4th root, it's definitely going to be less than 1 inch, because 1 inch is our larger diameter. It at least has to be smaller than that. So this makes sense so far. Okay, now let me just put these different torques into our new equation and see what we get. So diameter for A to B. Hold on, we can save ourselves a little bit of time here actually. Since we know that the inner diameter is going to be the same all the way through this bar, is it going to break more for 500 pound inches, or is it going to break under 13 pound inches? It's going to break under 13 pound inches a lot sooner. We are looking for the biggest possible D we can have without it breaking. Notice that a larger torque makes a smaller diameter, so we're actually looking for the smaller torque here, because if this one breaks, these are definitely going to break. So this is the one that I want to use. DBC to the 4th, 1 inch to the 4th minus 32 over pi. Now I'm going to be using my torque from up here, 500 pound inch. Alright, now I plug this into my calculator. Alright, so it's still to the 4th, but that number happens to be 0.5756, like that. And let's check our units. This is inches to the 4th, this is pound inches times inches, so we have inches squared, and this is pounds over inches squared, which means that those inches squared on the bottom here, we flip, invert and multiply. It means that we have inches to the 4th on top and pounds over pounds. So we have inches to the 4th everywhere. We can move on. Let's take the 4th root of that. It's to the 0.25 power. And we get 0.871 inches. Since I changed the numbers, that would be our answer.